All right, get ready, because today we're going deep on something pretty incredible, Google's file system. The system that's quietly handling a crazy amount of data every day for, well, pretty much all those Google services we use.
Yeah, and we're going way back to the beginning for this one. The original 2003 research paper, that's where Google first unveiled this game-changing system.
Back when big data was just starting to, become a thing, it's amazing to see how they tackled those early challenges. Honestly, they seem pretty intense even now.
Imagine this. You're Google. You're dealing with constant component failures, hard drives crashing, entire servers going offline. It wasn't if it would happen, but when.
Okay, so that's already a lot to handle. And on top of that, we're not talking about your typical Word docs or spreadsheets here, are we?
Nope, not at all. We're talking multi-gigabyte files like that's normal. Massive data sets that are constantly growing. It's like a fire hose of information that never turns off.
So how do you even start to build a system that won't just melt down under that kind of pressure?
That's where the brilliance of GFS comes in. They kind of flip the script. Yeah. Instead of trying to prevent failures, which at that scale is basically impossible, they designed a system that could handle them gracefully.
Okay, I like that. It's kind of like accepting that you're going to spill your coffee at some point, so you buy a really good travel mug.
That's a great analogy. Now, remember, we're talking about Google here. Huge scale. Hundreds of terabytes of storage, thousands of disks, hundreds of clients all trying to access this data at the same time. Staggering.
So what's the secret? How did they actually build this thing?
Well, at its core, GFS actually has a pretty simple architecture. You've got a single master server, the brains of the operation, and then an army of chunk servers, the worker bees, storing the actual data.
Okay, so one brain calling the shots and a bunch of worker bees storing stuff. Makes sense so far. But I'm guessing it gets more complex than that.
Definitely. And here's where it gets really interesting. Instead of storing files as one big blob, GFS breaks everything down into these huge 64 MB chunks. That's much larger than your typical file system. Think like 4 KB blocks, right?
Wait, 64 megabytes? That seems like asking for trouble. If one of those chunks goes bad, you lose a ton of data, don't you?
Well, that's where the redundancy comes in.
Yeah.
Each chunk is replicated across multiple chunk servers. So even if one fails, you still have copies of that data. But you're right to point out those 64 MB chunks. Might seem counterintuitive, but it's actually one of GFS's key innovations.
Okay, I'm all ears. Why so big?
Think of it this way. With smaller chunks, the master has to constantly tell clients where to find each tiny piece of the file. It's like asking for directions every few steps.
Ah, so with these massive chunks, the clients only need directions once, and then they can just stream a ton of data directly from the chunk servers. Gotta be way faster, right?
Exactly. It reduces all that back and forth chatter and keeps things moving smoothly. Yeah. Plus, those big chunks allow for persistent connections between the client and the chunk server, like a dedicated data pipeline. Makes it super efficient for streaming those huge files. Remember, Google, it's all about speed and efficiency, especially when you're dealing with things like searches and YouTube videos.
Oh, and all those cat videos. Can't forget about those. Okay, so we have this single master keeping everything organized, but how does it keep track of all these chunks? I mean, they're spread out across who knows how many servers.
Well, the master doesn't actually store the location of every single chunk replica. That would be a nightmare to manage.
So how does it know where anything is?
It relies on the chunk servers. When a chunk server starts up, it reports back to the master. It basically says, hey, I've got these chunks over here.
It's like a roll call for data. Chunk server 1, present and accounted for. Chunk server 2, reporting for duty.
Precisely. And it happens periodically. It simplifies things a lot. The master doesn't have to micromanage every single change in the system.
Smart move. Delegate, delegate, delegate. So the master is all about efficiency, keeping a high-level view of things. But what about making sure the data is correct? How do they ensure everyone sees the same information, especially with all this activity going on?
Now that's where things get a little wild. GFS uses what's called a relaxed consistency model.
Relaxed consistency sounds like something you'd see at a yoga retreat, not a file system handling Google's data. I'm intrigued, but a little nervous.
It's not as chaotic as it sounds. The key here is that GFS prioritizes speed and availability over strict consistency. It's like choosing to speed up a package delivery, even if it means the boxes might arrive slightly out of order.
So you're saying it's okay if things are a little messy as long as the data gets there quickly. Doesn't that risk corrupting files?
Not really.
Yeah.
Think of it more like a puzzle. where the pieces are in slightly different orders. All the data is there. It's just a matter of which bits got written when.
Yeah.
And the applications using GFS, they're designed to handle this.
Okay, so it's a controlled chaos. I'm starting to get it. But how do they manage this controlled chaos? How do they make sure things don't go completely off the rails?
They use a few clever tricks. One is called leases. The master, it grants temporary control of a chunk to a primary chunk server.
So it's like saying, hey, you're in charge of this chunk for a bit. Make sure all the writes happen in order.
Exactly. And to avoid bottlenecks, the data, it doesn't flow through the master. It goes directly between the chunk servers.
Cut out the middleman, maximum speed. Makes sense. But what about when multiple clients are trying to write to the same file at the same time? That seems like it would be a jumbled mess.
Well, that's where another trick comes in. Atomic record appends. This ensures that each client's data gets written at least once as a continuous chunk, even if others are writing to the same file at the same time.
So they might end up with duplicate data.
It's possible, yeah. But remember, GFS, it's all about throughput. A little redundancy is okay if it keeps things moving fast, and those applications using GFS are designed to handle those occasional duplicates.
So it's like a safety net, even if it means a few extra copies.
Exactly, and that's just the beginning. GFS has even more tricks up its sleeve.
Back again for more of the deep dive. We're right in the middle of this whole Google File System thing, or GFS. Last time, we were talking about those giant 64 MB chunks and GFS's, well, unique approach to consistency.
Yeah, how GFS is all about speed and availability, even if it means things get a little out of order sometimes.
Yes.
Keeping those data pipelines flowing.
Exactly. So now I'm wondering, how do they actually manage all those chunks and replicas? It's got to be like, I don't know, a massive juggling act with all those servers and the constant threat of failures.
It is, yeah. The master server definitely has its work cut out for it. It's constantly deciding where to place new replicas, rebalancing the existing ones, and how to clean up those orphan chunks that aren't needed anymore.
So the master is basically playing a never-ending game of Tetris, but with these, like, 64 MB data blocks?
That's actually a pretty good way to think about it. So when it comes to placing replicas, the master has a couple of goals. One, it wants to spread them across different racks of servers.
Ah, makes sense. Don't put all your eggs in one basket.
Right. If one entire rack goes down, you don't want to lose all your data. So spreading things out, make sure you have backups safely tucked away somewhere else. The second goal is to keep the workload balanced across all the chunk servers. Wouldn't be efficient to have one server overflowing with data while others are just sitting there.
Yeah, that's like having one cashier working overtime while everyone else is just, like, twiddling their thumbs. Not a good look. But things don't always go as planned. Hard drives crash, servers go offline, you know the drill. How does GFS handle those inevitable hiccups?
Well, that's the thing. GFS was designed with failure in mind from the get-go. It's built to be super resilient, and it uses a bunch of different techniques to make sure the data is safe and sound.
All right, break it down for me. What are some of their secret weapons in this battle against, like, data demons or whatever?
One of the most important ones is fast recovery. Both the master server and the chunk servers, they're designed to restart in seconds, no matter what happened.
Oh, so if something goes wrong, it's like hitting the reset button and boom, you're back in business. No waiting around for a long reboot or calling IT.
Exactly. And then, of course, there's the chunk replication we talked about before. Because each chunk has copies on multiple servers, even if a few chunk servers bite the dust, that data is still there, safe and sound.
Redundancy, redundancy, redundancy. But even with replication, couldn't you still run into data corruption? I mean, bits can get flipped, hard drives go bad, right? How do they make sure they're not serving up bad data?
That's where checksumming comes into play. Every 64 KB block of data has what's called a checksum. It's kind of like a digital fingerprint.
Okay, so like a built-in lie detector for data.
That's a really good way to put it, yeah.
Yeah.
If a chunk server detects a mismatch between the data and its checksum, it's like, hold on, something's not right here, and it reports the issue to the master.
And then what? Does the master send in a SWAT team of data recovery experts?
Not quite that dramatic. The master just starts a cloning process, copying the chunk from a healthy replica and replacing the corrupted one.
So the system can basically heal itself, no human intervention required. That's pretty neat.
And to make life easier for those humans who do need to check on the system, GFS has, well, a really comprehensive logging system.
Ah, yes, logs. Every engineer's best friend when things go wrong.
For sure. So the GFS servers, they keep detailed records of all kinds of events. Requests, replies, chunk creations, deletions, you name it. If something weird happens, engineers can go back and trace those steps to see what went wrong.
Like having a black box recorder for your entire file system. Pretty
Yeah.
handy.
And speaking of real-world experiences, one of the things that really struck me when I was reading the GFS paper was how honest they were about the challenges they faced.
Oh, you mean the parts where even Google engineers are pulling their hair out?
Exactly. They talk about running into specific Linux kernel quirks that, totally messed up their performance, weird hardware behavior, even issues with hard drives that didn't live up to, well, what they were supposed to do.
That's actually kind of reassuring. Even at Google's scale, they still have to deal with the same tech problems as everyone else.
Yeah, it really humanizes the whole thing, doesn't it?
Yeah.
But it also shows how incredibly smart and persistent they were. They didn't let those challenges stop them. They found workarounds, optimized the system, and built something truly remarkable.
They were pioneers, for sure, paving the way for how we build and think about these massive data storage systems today.
For sure. And, while most of us don't work with GFS directly, its influence is everywhere.
Okay, you got to tell me more. How does a system built for Google's data centers impact my everyday life?
Well, think about all the services you use every day. Cloud storage, streaming platforms, social media, all that. Behind the scenes, a lot of these rely on distributed file systems. And a lot of those systems were inspired by GFS.
So those ideas that Google pioneered, they're now trickling down and benefiting everyone, even if we don't see those 64 ME chunks.
Exactly. GFS showed that you could build these incredibly scalable, robust systems using, pretty standard hardware. And that has had a massive impact on the cost of storing and processing all this data.
It's almost like GFS helped, I don't know, democratize big data. It's not just for the big corporations anymore.
Exactly. And beyond all the technical stuff, GFS also teaches us valuable lessons about system design.
Okay, I like a good lesson. What kind of lessons are we talking about?
Well, one is that it's super important to make smart trade-offs. GFS, remember, it's all about high throughput and availability, even if it means giving up some consistency. Might not be the right call for every application, but it's definitely something you need to think about when you're dealing with data on this kind of scale.
So it's about finding the right balance, right? What works for Google might not work for everyone.
Absolutely. And another thing GFS shows us is the power of simplicity. The basic architecture with the single master and all those chunk servers, it's actually pretty straightforward. You don't need to make things super complicated to get amazing results.
Keep it simple, right? Sometimes the most elegant solutions are also the most effective.
Exactly. And that brings us to a kind of final thought-provoking question. We've seen how GFS is great in situations where speed and availability are super important. But what about when you absolutely need to make sure your data is accurate?
Like a bank's transaction system, you need to know every penny is accounted for, no room for error.
Right. In those situations, GFS and its relaxed consistency wouldn't work. You'd need a totally different approach. Something with more centralized control, maybe, or a system that's willing to sacrifice a little bit of performance for more stronger consistency guarantees.
Makes sense. So GFS was a game changer, no doubt about it. But it's not a magic bullet. It was designed for a specific set of problems. And to really get it, you need to understand what those problems are.
Yeah, it comes down to this. There's no one-size-fits-all way to build a data storage system. It all depends on your needs and your priorities.
Welcome back to the deep dive. We've spent the last two parts going pretty deep on Google's file system. This revolutionary system that can handle, well, an insane amount of data, way more than most of us can even wrap our heads around.
Yeah, it's been a wild ride. From those massive 64 MB chunks to that whole relaxed consistency thing, GFS is just packed with these innovative ideas that have really shaped how we approach data storage these days.
Definitely. But before we, wrap up our deep dive on this, I want to bring it back to the listener. Why should they care about a system built for, I don't know, Google's massive data centers? How does GFS have anything to do with their lives?
That's a good question.
Yeah.
And the answer might surprise you, because even though you might not be working with GFS directly, it's still all around you.
Okay, now you've got me curious. Tell me more.
Well, think about all the cloud services we use, like file storage, streaming platforms, social media, all that. Behind the scenes, lots of those rely on distributed file systems. And a lot of those systems, they were inspired by GFS.
So all those ideas that Google came up with, they're kind of trickling down and benefiting all of us, even if we don't see those 64 MB chunks ourselves.
Exactly. GFS really proved that you could build these incredibly scalable and robust systems using just regular everyday hardware. And that's had a huge impact on how much it costs to store and process all this data that we have.
So it's like GFS helped make big data, I don't know, more accessible. Like it's not just for the huge corporations anymore.
Right. And beyond all the technical stuff, there are also some really important, I guess you could say, general lessons about system design that we can learn from GFS.
Okay, I'm all ears. What kind of lessons?
Well, one of the big ones is the importance of making trade-offs. Remember how GFS is all about high throughput and availability, even if it means letting go of some consistency? That might not be the right choice for every situation, but it's super important to consider when you're dealing with data at this kind of scale.
So finding the right balance. What works for Google might not work for, everyone else.
Yeah, for sure. And another thing GFS really shows us is just how powerful simplicity can be. I mean, the core architecture, the whole single master server and a bunch of chunk servers, it's pretty straightforward. You don't have to overcomplicate things to get, really amazing results.
Keep it simple. Sometimes the simplest solutions are, well, they're the best ones.
And that brings us to, I guess, like a final question to think about.
Yeah.
We've talked about how great GFS is when speed and availability are, really important. But what about when you absolutely have to make sure your data is 100% accurate?
Like, imagine a bank's transaction system. You have to know every penny is accounted for, no room for any mistakes.
Right. In those cases, GFS and the whole relaxed consistency thing, that wouldn't fly. You'd need a totally different kind of system, maybe something with more control at the center, or a system that's willing to slow down a bit in exchange for, guarantees that the data is consistent.
Makes sense. So GFS was a huge step forward, no doubt. But it's not like some magic solution that works for everything. It was built for specific problems, and you have to understand those problems to, really understand the system itself.
It really comes down to this. There's no one perfect way to build a data storage system. It depends on what you need it to do, what's most important to you.
Well said. And on that note, I think we've reached the end of our deep dive into Google's file system. Hopefully you enjoyed this journey into the world of, well, massive scale data storage. And maybe you've come away with a little more appreciation for the incredible systems that, power all our digital lives.
Yeah, it's been great exploring this with you. And to everyone listening, we encourage you to, keep digging, keep learning. The more you explore these technologies, the more you realize just how amazing they are.
Until next time.